world here, Michigan and Park Hills. All right, so I think with that, it's time we get started. Welcome to the IBM Qiskit Live Quantum Seminar Series. I'm your host, Zlatko Minev, and today I have the pleasure to welcome Professor Meng Cheng from Yale University, who will talk about on the entanglement structure of Fracton Topological order. Hello, how are you, Meng?
I'm doing well.
Good.
Great.
It's good to see you. Welcome back. Where are you tuning in from?
From my house, I guess, basically.
Oh, wonderful. Yeah, near Yale. Before we pull up your slides, Meng, allow me to give a bit of a background. Meng is an assistant professor of physics at Yale University. He received his undergraduate degree from Nanjing University in 2013. Meng obtained his Ph.D. from the University of Maryland, where he studied topological superconductivity and its quantum information processing applications. Meng then moved to a postdoctoral research position at Station Q, Microsoft Research in Santa Barbara, and subsequently he joined the Department of Physics at Yale University in 2016. So we overlapped for a few years, but today we're going to do the seminar together. Meng is the recipient of many awards, including the NSF Career, the Alfred P. Sloan, and others. So with that, Meng, I'm going to turn it over to you, and the stage is yours.
Okay, thanks, Zlatko, for the nice introduction and also for the invitation. It's a great pleasure to speak in this seminar series. So today I'm going to talk about entanglement structure of Fracton topological order. So I think the mouse is, you can see my mouse, right?
Yes, I can.
Okay, all right. So first, let me begin by acknowledge my collaborators. So the work that I'm going to talk about today was done mostly in collaboration with my former graduate student, Arpit Dua, who's now a postdoc at Caltech, and Dominic Williamson, a former postdoc in my group, now moved to Stanford, and also Pratash, Joe Wang, and Isaac. Okay. All right. So before we get into the actual stuff, I'd like to first start by kind of placing what I'm going to talk about in a broad context. So by training, I'm a condensed matter theorist, but now it's more and more common and perhaps more accurate to call myself to say that I'm working on quantum matter, as many of us do. So it's still not easy to define exactly what quantum matter is, but I think it's something like you know it when you see it. Roughly speaking, it's the macroscopic system that exhibits interesting quantum effects, whose properties can have to be understood using quantum mechanics. And here I'm showing a very small sample of what we consider as quantum matter. You see, the more traditional quantum matter, such as high temperature superconductor or fractional quantum Hall effect. And more recently, these are probably, we can call them natural quantum matters. These are just things that happen in materials. And more recently, with advance of quantum technology, we also have more and more artificial quantum matter. So what I show here is one image for Rydberg atoms quantum simulator, and also transmon qubits. Okay. And I think we are all hoping that this will have a small to medium quantum device that will allow us to explore more quantum matter in near future. Okay. So with that, I'd like to kind of focus on a particular kind of quantum matter that, at least to me, that's the most interesting. These are quantum matter with what we call the highly entangled quantum matter. Okay. And for this class of quantum matter, there is a certain degree of emergent non-locality. Okay. And that non-locality allows this class of quantum matter to exhibit properties that are suitable for many quantum information applications. Okay. And even the name, the highly entangled quantum matter, suggests that the quantum information theoretic perspective is really fundamental to the understanding of this class of quantum matter. And this kind of interaction between quantum condensed matter theory and quantum information theory has really reshaped the way that we think about quantum matter through the past decade or so. Okay. So nowadays, it's almost impossible to talk about these things without using some ideas and languages from quantum information theory. Okay, so in particular, I would like to discuss a class of these highly entangled quantum matter, which are called topological matter or topological phase. Okay, so this is just a schematic picture from a review by Xiaogang Wen a couple years ago. And it turns out that this class of quantum matter has very close relationship with quantum error correction code. Okay, the property, this kind of emergent non-locality, is exactly what you need to do error correction. And this connection is what I like to kind of expound on later in the talk. So what I'm going to talk about is sort of a small example of how this sort of interplay plays out. Okay, all right. So let me be a little more specific and kind of define what I mean by topological matter. So if you search topological something today, or at least in the physics context, you'll see lots of different usages of the word topology. So I'd like to be a little more precise about what I mean by topological matter or topological phase. So as a condensed matter theorist, I'm thinking about the ground state property or low temperature property of a quantum many-body system. This could be some material, natural or artificial. And at the back of our mind, there's always some kind of lattice with, say, spins or electrons. And the system has a Hamiltonian with local interactions. Okay, so this is like the general setup of the problem. Okay, so I'll assume that the Hamiltonian has a spectral gap, meaning that if you look at the spectrum of this Hamiltonian, there's a ground state manifold with one or a few ground states. And then the ground states are separated from all the other excited states by a finite energy gap. And finite means that it stays there even when you take the system size to infinity, the thermodynamic limit. So the presence of gap kind of stabilizes the ground state, meaning that it's going to be robust with respect to small perturbations that you add to the system. And we are interested in the property of a phase, meaning that we're really thinking about a whole class of states, not a single state, but a whole class of states when you vary some parameters of the system. And here it's a schematic phase diagram. You have two parameters, alpha and beta. And by tuning these parameters, you get into different regions which share some common properties. So if the ground state here, you can tune it to a different ground state by just varying some parameter of the Hamiltonian, but without closing the gap, then they are in the same phase. Then we say that these 2 points in the phase diagram are adiabatically connected. And for two states which are the same, which are connected adiabatically, then the universal properties that I'm going to care about do not change. Okay, so really think about the whole phase and not just a particular state. All right. Oops. I guess this is something. Okay, so I guess.
I think you might have. Yeah, there we go. Good.
Okay. All right, so hopefully the screen's back on.
And maybe, Meng, before we sort of dig deeper into topological orders, error correcting codes, there was a little bit of discussion here in the chat. If you could give us a couple of examples of what you would qualify as good examples of, say, quantum matter in topological order, quantum matter things that are and aren't, so we know a little bit better where to draw the line between things that would fit this versus things that may look like they fit this, but maybe you'd like to exclude from the definition.
Okay, excuse me. So, well, I'll have one example shortly, but I guess it's easy to exclude things from highly entangled quantum matter. Many examples, many things we know in condensed matter physics, such as superconductivity, the ordinary superconductivity or magnetism, these are certainly quantum, right? They're certainly quantum matter in a broad sense, right? You need quantum mechanics to explain superconductivity for sure. You also need quantum mechanics to explain the origin of magnetism. But these are more classical compared to the kind of thing that I'm talking about here. These are less entangled, meaning that there's a classical order parameter. You can figure out the classical order parameter to describe what the state is. But for the highly entangled quantum matter, then you don't really have a classical description. Right? This state is truly quantum mechanical.
I see, and that would also include. Well, what about things like within the Hartree-Fock and highly correlated electron systems and.
Right. So of course, there you have all kinds of possibility. Where people are talking about possible highly entangled quantum matter like spin liquids in strongly correlated systems. So you might have examples there as well. But typically, if you describe some system using Hartree-Fock, then what I would think is that we are using mean field theory to describe this phase, and mean field theory gives you an order phase usually.
Great, thank you.
Okay, so I think hopefully it will become more clear when I discuss this simple example of topological quantum matter.
And maybe one more quick question from the audience here. For the picture we showed H0 and H1, this ground state and the gap can be very different, right?
Although the actual form of the ground state could be different. For example, you can imagine that if you write on a wave function, of course, it's going to depend on all kinds of details.
Yeah.
Right? And the size of the gap could change along this path. But as long as it stays finite, right? It doesn't close along the way, then we say that there's an adiabatic path between these 2 points.
Great, thanks.
All right, so I'll move on. So now I want to explain a bit why the topological order is naturally an error-correcting code. So here, the idea that we start from the many-body system. So you have lots of physical qubits, if you like. These are just the underlying spin, degrees of freedom, or maybe electrons in the system. But now with this Hamiltonian, we select some special states out of this exponentially large Hilbert space. And these are the degenerate ground states, okay, for topological order state. So you have this special states, the ground states, as a ground state of the many-body system. So you get these degenerate ground states, you put a system on torus or on a plane with boundaries and defects. And the defining feature of these topological order ground states is that they are locally indistinguishable. You cannot really tell apart one ground state from another just by doing local measurements. Therefore, in this sense, this process of going from physical qubits to the ground state subspace is essentially defining the logical qubits out of this many physical qubits, okay? And that's what you can consider as a quantum error correction code. So roughly speaking, this ground state subspace is a code space of this many-body system. Okay. And because these ground states are locally indistinguishable, so they are immune to local perturbations or local noise, and the gap kind of protects the ground states from decoherence. So you get, if you treat this code space, the ground state subspace, as a quantum memory, the lifetime is exponentially long in the size of the system. where here the psi is some characteristic length scale determined by the gap. Okay, so now let's discuss a little bit, perhaps the simplest example of topological order state, the toric code. So the name already tells you that this was invented as error correcting code. Went back to 1997 by Kitaev. So the system is a two-dimensional lattice, a two-dimensional square lattice, and we have qubits or spin 1/2, if you like, sitting on edges of this lattice. Okay, and there are two types of interactions or stabilizers, if you like. This is a stabilizer code. Two types of interactions. One type of interaction is a vertex term. They just multiply the Pauli X operator on the four edges coming out of one vertex. Okay, so that's one term. And the other term is a plaqué term, that we multiply the four Z's around one plaqué. So you have these two types of terms. Since they are just products of Pauli operators, they square to 1, and it's you can check that all terms commute with all the other terms. Okay. So the Hamiltonian is simply just summing over all these terms for each vertex and for each plaqué. Now, this is a commuting projector model. Since each term commutes with all the other terms, so you can solve it exactly. And when you put this Hamiltonian on the torus, or in other words, you put periodic boundary conditions on this lattice, you find that there are 4 degenerate ground states, and these 4 ground states are locally the same. If you look at just a local patch of these 4 ground states, they look exactly the same. However, they are different globally, and the difference between them can be picked up by thinking about these long operators, long string operators that wrap around the whole torus. So this red line here denotes a logical X operator in this ground state subspace or code space, which is just a product of Pauli X along a certain path on lattice. And then correspondingly, there's a logical Z operator, which is a product of Z along some other path on lattice. Okay. So to distinguish these ground states, one has to look at these non-local operators. No local operators can detect the difference. So if we unwrap the torus, we really draw it as a square, but imposing periodic boundary conditions, well, we see that there are these string operators. And importantly, these string operators are deformable, meaning that as long as this operator wraps the whole torus, running from one edge to another edge, and these two edges are identified, it doesn't really matter where they are. You can move them around, or you can deform them, wiggling into some shape that has wiggles. It doesn't really matter. All of them have the same effect in this ground state subspace. Okay, it happens again, so I guess I have to. I'm sorry that somehow my keynote is doing this weird thing.
That's okay.
Yeah. All right. So on previous slide, we were just looking at closed strings wrapping around the whole torus, but you can also cut the string open. And when you cut them open, you get excitations at the two ends of the strings. Okay. For example, if you have a product of Z operators along this path, and at these two sites, then these two, the vertex term at the two ends are excited by this operator, but nowhere else on this lattice are excited. So you get the two excitations, and they are called anyons because they have non-trivial braiding statistics. And in the language of error correcting code, these are the errors that you don't want to see in a code, okay, because they violate the stabilizers, the terms that stabilize the ground state. Well, this is again a bit strange, but let me try this. Okay, so another feature of this, as I already mentioned, is that these strings are deformable. So you can push the strings sideways, and it creates the same the same wave function, to create the same state, excited states. Okay. And the implication of this is that you can actually move these particles, move these excitations around, any way you like in the lattice, because the strings are perfectly deformable. These excitations are free to move. They are mobile.
And could you just comment on the edges of the string and moving the edges?
The edges of string, you mean the two endpoints?
Sorry, the endpoints, yes.
Yeah. Okay, yeah, so you can easily extend the string by putting another Z operator, and that will move the endpoints to the next location. And you can move it in all possible directions on lattice. So that's what I meant by the string deformability of the string implies that the errors, the endpoints are completely mobile on lattice.
Excellent. Thank you.
Okay, so far everything's at zero temperature. So we are talking about the ground state of the system. And you may ask what happens if you heat up the system. So far topological order is really at zero temperature, but we can heat it up. But once you heat up the system, it turns out that for example, for toric code, there's no finite temperature phase transition. You're just going to heat up until you get to the infinite temperature, which is sort of a boring situation. Okay, and there's no thermal transition in between. And physically, what happens is that when you heat up the system, you get a finite density of quasi-particles, just following the Boltzmann distribution. And with a finite density of quasi-particles, you have a finite density of errors in your code. And these quasi-particles can move around and basically destroy whatever information you store in the system if you don't do any active error correction. Therefore, without active error correction, the memory lifetime now becomes system independent, right? It's just determined by this Boltzmann factor or the Gibbs factor, the inverse of the Gibbs factor. That's the density of the quasi-particle. So we lose this nice feature of exponential protection by the system size, and now it's just something constant. So another equivalent way to formulate this is that there's really no topological order, at least in this example, at finite temperature. And although it's not exactly the same, but it's more or less equivalent to say that there's no self-correcting quantum memory in 2 dimensions without doing active correction.
And that's a really important point. Maybe a quick question from the audience here, Meng.
Yeah.
Could you please tell about the Z2 symmetry? What exactly does that mean for the toric code?
Z2 symmetry. Well, so maybe let me go back. Oops. I have to really fix this issue, but the toric code has many symmetries. So you have the symmetries of all the product of X and all the product of Z's, but they don't really play any role. This topological order exists without any symmetry, doesn't really require any symmetry to protect them. If you have an interesting symmetry, sometimes you can these symmetry. So that's one thing, that the topological order doesn't really need any symmetries. But if you have a symmetry, the symmetry may act on the topological degree of freedom in some interesting way. Okay, not in this example, but maybe in some other example that does happen. And that may give you some way to, for example, manipulate the topological ground states. But the symmetries do not play a role in this example or in the talk. All right. Sorry that somehow my keynote is not collaborating with me very well, so I have to do this. All right, just to quickly summarize, so topological order, it has locally indistinguishable ground states on torus or on some other manifold, and that basically is a key feature of the error correcting property. And excitations, localized excitations have low energy. In the 2D case, you have these particle-like excitations. It's a bug for quantum error correction as a code. No, you don't want these. But I just quickly mention that it's a feature for topological quantum computing, which uses non-abelian excitations to store quantum information. Okay. But in any case, the topological quantum order goes away at finite temperature if you have a particle like excitation in your system. And another quick comment is that in 2D, we have a pretty good understanding of what topological order, what kind of topological order exists. It's described by a nice mathematical theory of a tensor category. Okay. All right, so now I want to switch to the Fracton models. This is the main actor of this talk. So I'd like to give some examples of Fracton models. So I believe the first Fracton model was written down by Claudio Chalmon back some 15 years ago, or even earlier, and then also some work by Bravi et al. And another important class of example is the cubic code written down by Joan Haah. Okay, so compared to, for example, the Tori code that I discussed earlier, they share lots of common features. For example, you also get topologically protected ground states on torus. There's a degeneracy of ground states which are all locally indistinguishable. But what's unusual is that the number of ground states you get grows with the size of system. Recall that in the Tori code case, it's always just 4. Right? No matter how large the system size is. And the related fact, which gets these models a name, a fracton, is that quasi-particles or the excitations have restricted mobility. They can only move in certain directions, or they cannot move at all. Okay? And fracton refers to excitations or these quasi-particles which do not move at all. So these two features sort of distinguish the Fracton models from the more conventional topological ordered phases. And that's one reason that we are interested in understanding these models. So let me just discuss a couple of examples more concretely. So the Haah's code is a model that defined on cubic lattice in 3D. Okay. So the detail does not really matter that much. It's a model where you put 2 qubits per side, and you can write down these interactions. Okay, and you can check that all these terms commute for each cube. There are 2 terms, and all these terms commute. And here is a plot of number of ground states, or really log 2 of the number of ground states, or you can say this is the number of qubits encoded in the ground state subspace, how that number grows with the size of the system. And the system is a L by L by L lattice with periodic boundary conditions. You can see that the number fluctuates wildly as you change the size of system. There's an envelope that is kind of nice. The envelope is actually 4L minus 2, and you hit that envelope if L is a power of 2. But for example, if you change that just by 1, the number of ground states drops from, already the number of encoded qubits drops from 4L minus 2 to 2. So you have these wild fluctuations of the number of ground states. And if you look at excitations, you see an interesting pattern. For example, if you act on the ground state by an operator xi, x is poly x on the first qubit, I is identity on the second qubit, you just put that operator on some site, then you create 4 excitations. You have 4 violations of the cube terms. There are 3 you can see. There's 1 in the back, invisible in the back. Okay, so you create excitation in this kind of tetrahedron pattern. And if you try to isolate these excitations, if you want to move them apart, the only way to do that is to keep doing this, but following this sort of tetrahedron pattern, and you always get 4 cube violations. You can try to eliminate as many as possible, but you always end up having 4 violations at the corner of a much larger tetrahedron, okay, if you apply many such operators in the middle. So there is a particular very rigid pattern of to create excitations. You cannot move them. We cannot just take one of them and move it around like what we did in Tori code. If you want to move one, well, you sort of have to move all 4 of them together. Okay, they move collectively. Or you can move one by creating more excitations. So it's proven by Haah that there's just no string operator, like the one that we saw in Tori code. There's no such string operator in this model. This is the only way to create excitations and sort of move them. Okay. And the reason that Haah studied this code is exactly because the excitations, the errors are hard to move. So you can expect that this code will have a much better much better performance as a self-correcting quantum memory. It turns out that it's not quite a self-correcting quantum memory. The memory lifetime, you can get to much better scaling compared to the Tori code. Now you get some constant over t squared in the exponential. Okay. Of course, the details depend on what exactly how you decode, what kind of decoder you use, but roughly that's what you get. You do get a big improvement, although it's not really self-correcting yet. This is very annoying. And there are other kinds of fractal models. So I'll quickly flash through one more. So this is called Sierpinski's fractal spin liquid. Was written down in 2 papers. Okay. Again, the details do not really matter, but let me just quickly flash through like what properties we see in this model. So this model is a bit different from Haah's code. Is that you get particles moving in one direction, and we call them line-ons. So you have a particle, you can move them along the z direction in the way that I draw it, but you cannot move it in the xy plane. The only way to move or to create particles or these excitations in the xy plane is to create 3 of them in this pattern at once, and then make this triangle larger and larger. Okay. So in a way, the pattern, the operators you put in to isolate 3 excitations at the corner of this triangle is like this fractal shape Sierpinski's triangle. Okay. So by applying operators in this pattern, you can create 3 excitations at the corners. So that's somewhat similar to what happens in Haah's code, although it's somewhat different because that pattern now it's in the 2-dimensional plane. So I've already used some of these terminologies. It's just nowadays in this community we talk about we want to distinguish particles with different kinds of mobility. So fracton is a particle that just doesn't move at all. There's no operator that can move a fracton without creating more excitations. And line-on is a particle that moves along a line, and plane-on is a particle. Obviously, it's a particle that moves in a plane. And we don't really have a name for a complete mobile particle. Just say, all right, that's mobile. So following this pattern, fracton probably should be called a point-on, but no, that's what it is. And we also have a very rough and purely phenomenological kind of classification of these models. We call them type 1 and type 2. Type 2 is a model where every excitation is a fracton, meaning that they're all immobile, completely immobile. And if it's not type 2, then we call it type 1. So it's binary. It's either type 2, meaning everything's immobile, or type 1, meaning that something is mobile. Okay, so this is one more. This is probably like a much easier model, not easier in terms of analyzing the mobility structure and the topological order. It's called the X-cube model, and it has all kinds of particles. So in the previous 2 examples, you get the particles, they all have the same mobility. Either you get fractons in Haah's cube code, or you get line-ons in this fractal spin liquid. And here is a model where you get particles of different mobility. Okay, you get a hierarchy of particles. So maybe let me not go really into detail of this model. It's again a stabilizer model. Each term is a product of Pauli operators, and they all commute. And the CSS code, meaning that's either the product of X or product of Z. Okay. And the excitations of the cube term, the violation of cube term, is a fracton. And this time you can create it. You can create 4 of them at the corner of a membrane of a rectangular sheet. Okay, so this is geometrically somewhat easier to think about than these fractal shapes. And it also means that if you take 2 of them, now they can move along the direction perpendicular to whatever that connects them, the vector that connects them. Okay. So you get a single cube violation as a fracton, and you also, a pair of them, a dipole, is a planon, turns out. And looking at the other sector, if you violate one of these Z terms, you actually get a linon. So you get both fractons and planon and linons. Oops. All right, so I've talked about several examples of topological ordered systems. Okay, and you might ask, since they are nice, they have these nice properties, maybe we would like to classify the possible topological order. Right? What are their properties? This is a really difficult question, and there has been a kind of a program of trying to come up with such a classification, at least for the gapped phase of matter, in the past decade or so. There has been a lot of progress. If you make the assumption that these gapped ground states can be described by something called the topological quantum field theory, this is a strong assumption, and certainly not obvious that something you write down on a lattice can actually be described by a field theory and the topological quantum field theory. Okay. But with that assumption, you can actually come up with, this is, of course, takes a lot of work, really a combination of many years of work from many different people. But we now have a pretty good understanding of what topological ordered phases there are, assuming this quantum field theory description. And here is basically a very short summary of what we know about them. But I won't explain what each of these things mean, but roughly, we have a pretty good understanding of what each of these, what the properties there are and how to describe them. You can also study various properties such as the symmetry, or what happens if you have boundary or defects. These are interesting from both from kind of the quantum matter point of view, also from the quantum information point of view. And many of them actually have very explicit construction or codes, even maybe they are complicated. Okay, but then there's a huge outlier of this program. This fracton topological order doesn't fit this description at all. Okay, so they are not described by any kind of quantum field theory, at least not in the conventional sense. So that's another reason that fracton topological order is interesting. So now even quantum field theorists, high-energy theorists, are getting interested in this class of models. All right, so I've talked about fracton topological order, and now I want to look at fracton topological order from maybe the lens of quantum entanglement. Okay. All right, so just a quick review of how quantum entanglement comes up in a many-body system. Well, if you have a many-body system, this is meant to be like a 2D material. You can look at a region in the system, a subsystem A, and the rest is the complement A bar. And we can ask, what is entanglement entropy of this subsystem? Right? And the entanglement, because of local interaction, the entanglement all comes in, at least for the ground state. This is meant to be a ground state. That all the entanglement, naturally, appear at the boundary between this A and A bar, because that's, you can imagine there are lots of Bell pairs across a boundary, and these Bell pairs entangle the subsystem A with complement. But if you move far away, then there's no entanglement between the two systems. This is what typically happens in the ground state of a local Hamiltonian. So more precisely, can define entanglement entropy as just the Van Neumann entropy of the reduced density matrix for this subsystem A. And we expect, although I don't think it's proven, but we expect that the entanglement entropy grows linearly with parameter of this region, the length of the boundary. Okay, but in 2D, there's an interesting correction. This is the leading term, and the next term is a constant, the negative constant. Okay. And we sometimes we say that this area law term, this term that proportional to the parameter of this region represents a short range entanglement, because they kind of come from small entangled pairs across the boundary of the system. But this minus gamma cannot be explained by such short-range entanglement, so it's something more non-local, and it's really a global feature of the system of the ground state. And gamma is called the topological entanglement entropy, first observed by in these two works. And it's really invariant of a topological order system. So I just want to quickly mention that kind of a side work that we stumble upon while studying this fractal model is that sometimes you get spurious topological entanglement entropy. Of course, there were earlier examples, but what we find is perhaps a simple and somewhat unexpected one. Is that you can, and the reason that they come up is that we don't usually want to directly look for this term from how the entropy scales with the length of the system, the length of the boundary. We want to have some better way to compute it. And these papers put up some ingenious constructions which cancel out the area law terms and also contribution from a corner, and just give you the gamma, the topological piece of the entanglement entropy. Okay. So by thinking about several regions like this and adding and subtracting the entropies, you can directly extract a constant. And usually this constant can be identified with a topological entanglement entropy. But there are situations as simple as a cluster state in 2 dimensions, or the cubic code, etc., where the gamma prime is not equal to gamma. And the reason for these spurious entropies, topological entropies, that there are certain rigid subsystem symmetries in the system. Okay, so this just want to quickly flash. All right. So with this difference between the short range and long range entanglement, we like to have a way to kind of distill the long range entanglement. Right? We kind of want to filter out the short range entanglement because that's not particularly interesting. Like to figure out the way to have a way to kind of look for this long range entanglement. And in physics, in STAMAC on quantum field theory, there's a way to sort of go from what happens at short scales. You have a Hamiltonian, you can write down Hamiltonian, then that really gives you what happens to a system at very short scale, to much longer scale, infinite decisive limit or thermodynamic limit. And this is called the renormalization. Okay? And the idea that was the idea is to going to long scale step by step. Okay? And during this procedure, you filter out what happens on shorter scales. So you can imagine this is sort of zooming out of a picture and just get the broader features and neglecting the details at the finer details at short scales. Okay, And when you reach the infinite size limit, it's called RG. The fixed point are then under the renormalization group transformation. So this is very annoying. Apologize. So let me.
It's because you have a 2D screen and not a 3D one.
Yeah. It's
not self-correcting.
Yeah, you have to do menu correcting. So. All right. So let me describe this procedure, this entanglement. Well, so what we want to do is we want to have a normalization procedure that kind of filter out short-range entanglement. And this was proposed by first, I think, as far as I can tell, it was first proposed by Giffrey-Vidal. So here's a schematic picture of how that goes. Is that let's say you start from some 1D spin chain. So I'm not going to specify what exactly the Hamiltonian. It's just a kind of illustration of this procedure. You start from 1D spin chain, and the procedure always starts from coarse graining. For example, we group these two spins as one, or equivalently, we enlarge unit cell. Okay, and then we apply some circuit, if you like, some unitary circuit to remove short-range entanglement, to remove the short-range entanglement as much as possible. Okay, and then maybe after this procedure, there are some degrees of freedom which are completely disentangled from the rest of the system, and then we can kind of just discard these disentangled degrees of freedom and focus on the rest. Okay, and typically after this procedure, you get a coarse-grained system of larger unit cell, okay, and fewer degrees of freedom, and then can keep doing this until we reach the infinite size limit. So this is called entanglement renormalization, and the key here is to remove the short-range entanglement, also known as wave function normalization, because it's operating on the wave function. So you can do this for a toric code. And you can do this explicitly, step by step, and writing down all the unitaries you need to remove the short-range entanglement. We start from coarse graining. We enlarge a unit cell, grouping, for example, these 4 sites as one. Okay, now it's a larger unit cell. These four sites are in one unit cell, and can do local unitaries, remove disentangled qubits. And once you kind of zoom out, you get a lattice, and you end up with a lattice of 4 sites now, because now you just have these 4 sites. Okay. And it turns out, quite remarkably, in the case of toric code, once you do all these and remove disentangled qubits, the Hamiltonian on the coarse-grained lattice takes exactly the same form as the Hamiltonian that we start with. Okay. So this is really nice. It tells you that toric code is actually a fixed point under this kind of entanglement renormalization. Okay. And what this really means is that if you have a toric code, say on a Lx by Ly system, you can grow this toric code. You can grow it to a system of double the size of the system. You can grow it to a size 2L by 2L by basically a local unitary. Of course, you have to add some degree of freedom just to make up Hilbert space dimension. Right? You have smaller number of qubits here compared to this larger size, but all you need to do is to bring in some trivial qubits. These qubits, they are not entangled. They're just in the product state, and you can bring in such a product state of qubits, and then apply some local unitary to grow the toric code to double the size of the toric code. Okay. And these are the things that we discarded in the entanglement RG, the disentangled degree of freedom. So in one sentence, toric code can kind of grow by absorbing just some trivial qubits. You don't need to supply additional entanglement. Okay. So now let's apply this entanglement RG to qubit code. This was done by Haah back in 2013. Now it's very different. If you want to grow a qubit code, this is now a 3-dimensional model, so it's L by L by L. If you want to, say, double the size of the system to 2L by 2L by 2L, of course, you need to add some stuff, otherwise the Hilbert space dimension doesn't agree. But it turns out that this additional piece that you need to add cannot just be some trivial product state of qubits. This additional piece you need to add also has to be highly entangled. Okay, and this additional piece is called the qubit code B. So it's a ground state of a different model, which is also a fractal model. But the point is that this additional stuff has to be in a highly entangled state to get to this qubit code on a larger size. Okay, so in this case, all right. So in this case, to grow the qubit code, you actually need to supply a highly entangled quantum state, not just some trivial product state. Okay, so you need some non-trivial entanglement resource to do this. Okay, and here I represent this procedure schematically by drawing this picture. So CC stands for qubit code. And when you do this, I think I have a typo here. It's not CCB on the right-hand side, it's just CC, qubit code. The qubit code under RG is splits into two things. If you read the picture from right to left, then you get another copy of, this is, sorry, I guess I'm talking about the next slide. Sorry for the confusion. So, okay, so let me maybe restate this is that for a qubit code, if you want to grow it, you need to add a second, you need to add a copy of this qubit code B, a different model. But for the qubit code B, you can also ask the same question. It turns out that to grow it, you just need a copy of itself, but still you need something highly entangled. All right, so I draw this diagram to represent how things change under this renormalization. The qubit code splits into a copy of itself under RG and another qubit code B. Okay, that's represented by this arrow here that just goes back to the qubit code itself, and then another arrow comes out that tells you that a qubit code B is split out. And for qubit code B, if you do RG, you get two copies. So that's the two arrows here. It's just a picture to summarize what happens under the entanglement RG. Okay, so we'd like to understand more generally what happens for the many other models and try to kind of see some pattern and some structure for the entanglement renormalization. Okay. So we carried out this exercise of entanglement RG for many other models. It turns out that Haah actually found 18 different models from computer search. And the qubit code is the first one of these models. It's the most symmetric one, so it's the most well-known, but there are 17 other models. And we carried out the RG for the other models, and they all have different behaviors. Some of them just replicates itself, just splits two copies of the same code, for example, for these models. And some models have different behavior under different directions. If you double the size in X direction, in this model, you just get a copy of itself. But if you double size in the other direction, you get bifurcating, or you get two copies of the model, etc. And then you might even get more complicated RG. For example, for these models, you get a copy of self, you get a B model, which is a different model that self replicates under RG, and you also get a stack of toric code. So STC here means stacks of toric code. So you have a variety of different behaviors under RG. Okay. All right. So this is like a little numerical experiments, a lot of work by Arpit, but so we like to kind of summarize some of the features from this list of RGs. Okay, and one connection we like to build is that how do we tell the RG behavior or model without actually figuring out the details, without actually calculating the RG? You can do it, but it's actually not easy. For each model, you have to kind of start from scratch and do a lot of trial and error. There's not really a systematic way to construct the RG. Okay, so just to give one example. So how am I doing on time?
I think we are coming up on the hour, but that's okay. We can maybe go through your example.
I have like a few more slides.
Great.
All right. So let me discuss one example of this, this whole list of RGs. Okay, this example is a cubicle 11, which is which lies in this complicated case where you get different kinds of you get two things out. We actually get three things out: a copy of this model itself, stack of toric code, and cubicle B. Okay, and this is how the ground states, number of ground states change under RG. So the cubicle 11 model turns out, if you just look at excitations, it supports fractons, linons, and planons. Okay? And the cubicle B itself is a linon model, meaning that the lowest mobility particle is a linon. So the fact that you get planons kind of suggests that planons are naturally just toric codes, right? Planons, in this world of Pauli stabilizers, a planon could probably remind you of toric code. And indeed, that's what we observe, is that you get planons in the YZ plane, and if you do RG in that plane, you can extract. If you do RG in the X direction, you extract these toric codes. So, sorry again. So first, let me perhaps just summarize the common pattern of entanglement RG for the fractal models. So for all of them, we see that in order to grow the model, say, to double the size of the system, you need one or maybe more models, highly entangled models. And all these other models, the resource you need to grow the system are self-bifurcating, meaning that these additional pieces you bring in, they will just split into two copies of itself under RG. Okay, so everything that we have looked at follow this pattern. This model that we want to do RG on is called the A model. So A model splits into another copy of A model plus a number of B models, and these B models are also in highly entangled ground state. Okay, and these B models always splits into two copies of the same model under RG. So this is a common pattern for all the stabilizer models that we have checked. So these self-bifurcating B models serve as entanglement resources when you try to grow the system. And we can actually build some link, just from looking at this different behavior, we can build some link between how the system behaves under RG with the mobility of the particles. And this was actually a pretty ambitious goal of ARPIT, to establish some kind of structure theorem for stabilizer codes. We actually have a very nice structure theorem proven by Bombing and Haah, that if you have a 2D Pauli stabilizer code, it's always equivalent to just copies of 2D toric codes and plus some uninteresting stuff under a Clifford circuit. Okay, so we kind of understand all the 2D Pauli stabilizer codes, at least a universality class of them as a topological order. Okay. However, we don't expect such a nice result can generate to 3D because we already know there's a whole variety of models in 3D, even for the Pauli stabilizer models. What we can hope for is that we can establish some kind of entanglement structure theorem, meaning that we can say something about how systems behave under RG just by looking at what kinds of excitations you have. Okay. And this is what ARPIT's result, not published yet, is that if you have a particle that is completely mobile, then this particle basically sits in a 3D toric code. It's not this fractal model, it's just a really straightforward generalization of toric code to 3D. And this is one of these topological models that are described by TQFT, topological quantum field theory. If you have a planar, necessarily a 2D Tauri code comes out once you do the RG, and if you do it for the whole system, you actually get a stack of Tauri code in the plane that hosts these planars. Now, these are the kind of easy ones. Easy means that you can actually say something definite about what comes out. Things stop being so nice once we get to linons and fractons. So all one can say is that if you have a linon, you can extract the linon or fractal model, and if you have a fracton, you necessarily have a fractal model comes out from the RG. It could just be the model itself. Okay, so it's less specific in the last two cases. However, we do have this very definite outcome if you have a planar. All right, so this is pretty much all I want to talk about. I just want to mention that if we go beyond polystabilizers, polystabilizers are nice. They are easy to write down, to analyze, and perhaps easy to implement if you think about these quantum processors. But if you go beyond polystabilizer, there are many other different models which have exotic behaviors. I just want to mention one of them, that is models that support non-abelian fractons in 3 dimensions. And there are other models that of similar feature that I don't have time to discuss. Okay, so that is all I want to discuss. So I'll just put up the slides here, and these are the references. And thanks everyone for tuning in.
Thank you, Meng. This was a great talk. Thank you very much. We've had one of our liveliest discussions here in the chat, so that's great. Maybe start off with a few questions I've sort of accumulated from your talk from the audience here. Could you speak to the entanglement of the topological phase ground state? So there's a question about, are they maximally entangled, and in what sense, and sort of what is the interaction of entanglement monogamy that plays in here, and how that affects these constructions?
Okay, so let's maybe one by one. So there's something about maximal entanglement.
Right.
Well, so I guess if we think about these two regions, A and A bar, they are certainly not maximally entangled, right? Otherwise, you would get a entanglement entropy proportional to the volume or the area of this region, the volume of A, right? And that's what you typically observe. Well, I guess not always maximally entangled, but you do get volume scaling in highly excited states of these systems in the many-body system. But in the ground state, we only get entanglement along this entanglement cut, right? The cut we draw to kind of define the subsystem, and that's because of the local nature of the interaction, and also we are looking at the ground state, which is a very special kind of corner of Hilbert space. So I guess the answer is that it's not maximal entanglement, at least in the literal sense. I hear you mention something about monogamy. Can you repeat that question again?
Oh, I think there was, in the discussion, it came up that, because of entanglement monogamy, because you can't have, one qubit entangled with everyone else. If you entangle more with one, you have to give up entanglement with others, right? That imposes certain restrictions on what you can do, and
yeah, right. That there is a maximum amount of entanglement you can generate for, say, qubits in A, right?
That's right. Yeah, so not sure if that's much of a concern in these at the moment for you, but I think there was some interest around that. And now the other question we had here was coming back to the boundaries, especially around the 3D and periodic, and I think most of what we talked about at the theory level, at the analytical level, typically assumes these periodic boundary conditions. Now in practice, usually you don't have that. Could you comment on what you might lose relative to periodic, or do you lose, and sort of what the effects of the boundaries are in for the arguments that we've had so far?
Okay, yeah, that's a great question. So of course, indeed, as you said, it's most convenient to analyze these models to exhibit the topological orders to put them on a periodic boundary condition, so you get a torus. Now with boundaries, things are somewhat more complicated because now it depends on what exactly happens on the boundary conditions. Okay. So in one case, for example, in the Parry code case, oops, let me actually go back to the Parry code slide. Where is that? So if you just treat this as a open system, it's like a disk or just a rectangle with no periodic boundary condition, then for one choice of boundary condition, you don't get any degenerate ground states. So certain choice of boundary condition could kill the topological degeneracy altogether, even though the system is still topological order. You just don't have degenerate ground states for some choice of boundary condition. But for some other choice of boundary condition, you might get you might get topological degeneracy again of a different nature. Okay, so it all depends on boundary condition. And just maybe to kind of a related fact is that if we think about the actual surface code, at least if I understand it correctly, then the qubits are not encoded on a torus, right? You don't actually build a torus in a lab. Well, that's not realistic. What you do is that you create some boundaries in the plane. So you just have a plane and you create some boundaries. And it turns out that if you have multiple, say, boundaries inside multiple disks, you just remove that disk and you create a boundary. If you have multiple boundaries, you also get topologically protected ground states. And you can use these ground states associated to the boundaries to do quantum information processing. So the short answer that it really depends on what you do on the boundary, and it could go in either directions. You could kill the degeneracy, or you could have more degeneracy, depending on what exactly the configuration of boundary and the boundary conditions.
Wonderful, thank you. And since there was a lot of discussion around this one as well, maybe I'll throw this out. Coming back to the very beginning of the talk where we talked about what is quantum matter and what is not.
Yeah, wow.
I know there's no consensus here. and Manu has been very helpful in have this discussion. But I was wondering, what was your opinion on BECs? Is that quantum enough in the sense that you can describe it well with a product state, so you can do a mean field description,
right?
As long as you don't have vortices, it's a product state.
That's absolutely right. So yeah, when I prepared the slide, initially I had a couple of I actually had the picture of BEC in the middle. It's probably more familiar, and it's certainly quantum. There's no question. It's quantum mechanical. Right? You have to describe it using quantum mechanics, but it's so I eventually I didn't include it just because of I want to have some other pictures, and for whatever reason. But as you said, it has a mean field description, so it's not a highly entangled quantum matter. It's still quantum. Yeah.
Got it. Not highly entangled quantum matter. Okay.
Maybe not highly entangled, right? Yeah. So I guess there's not really a very clear-cut definition of quantum matter yet. Even in this phase diagram I show, there's superconductor, which is very mean field-like state. You have this antiferromagnetic insulator in this Kupris phase diagram. So these are all mean field states. Right.
Got it.
Yeah.
And okay, so maybe second to last question. Do you? This is a question from the audience. Do you have notes or a book on topological quantum computing from the basics that you like or would recommend for people who are new to this field?
So not. Let me think. This.
Okay.
Yeah, I think what I can recommend, for someone new to this, there's a kind of lecture note by Alexei Kitaev. think it has some titles like Introduction to Topological Phase and Quantum Computing, something like this. It's not very long, and it starts from basics, basically explaining all details about toric code and also Majorana wires. And I think that's a good entry point. If we think about books, there are not many books written on this subject yet. I think there's a recent book, maybe a few years back, by Xiaogang Wen, Xie Chen, and maybe a few others, that really takes a quantum information perspective on this subject, on quantum matter and also error correction, etc. So that might also be something that worth taking a look at.
Got it.
I cannot really remember the title of the book, but I think it's quite so it's something like quantum matter and quantum information has
yeah. All right, wonderful.
It's really available on archive, so yeah, both are those you can find on archive. The two things I mentioned, the two materials.
Great. Well, I think with that, I think I'll leave it if you have any final words to say. But I think this will be the wrap up of the seminar for this week.
Okay. Well, thanks all for attending. That's
great. Well, thank you, Meng. Thank you, everyone, for tuning in this week. It was our pleasure. Thank you for all the discussion. Guan Yu, thank you for answering all those questions in the comment chat box. And I think with this talk will stay live on YouTube and recorded, so you can go back and rewatch it. Subscribe to the YouTube channel. And otherwise, we will see you next Friday at noon Eastern Time. Looking forward to it. Thank you, everyone. We'll see you next week.